be periodic. So we look at this blue curve here, f of x, or g of x is equal to the arcsine of x. Now the arcsine is only defined for x equals -1 to x equals 1. However, if we still do g of f of x, which is the arcsine of the sine of x, we will still get a periodic function, which is this red curve here. Now this is a sawtooth function, and a special property of this is that from 0 to pi over 2, the slope of this red curve is always 1. And from pi over 2 to 3 pi over 2, the slope is always -1, and that will repeat. And for periodic functions, we can compute a Fourier series for the periodic function, which is as we go and take more and more terms, this will approximate that function. And so what we did was, for the arcsine of the sine of x, we knew it was a sawtooth function. So we can compute the Fourier series, or what we did was we went into a mathematical handbook for Fourier series, and we just looked under sawtooth functions, and we found this series right here. You notice pi appears in the denominator right there. And so what we're going to do with this, well, first, if you take just the first term, 4 over pi times sine of x, you can already see it starts to closely approximate the actual arcsine of the sine of x. Then this red curve is 2 terms, and then the green term, or the green curve, is if you take the first 3 terms. You can see it more closely starts to approximate the actual curve, which is black. And so what we're going to do with this is here we have h of x, which is just f of g of x, equals arcsine of x, and then on the right side we have the Fourier series. And as explained earlier, from 0 to pi over 2, the slope of this curve is just always equal to 1. So we know that at x equals pi over 2, the value of the function will be pi over 2. And so at h of pi over 2, that's just pi over 2. But then for the right side of this equation here, even though we don't know what pi is, we know what the sine of pi over 2 is, sine of 3 pi over 2, and so on, based on how the sine is defined. And so if we plug in these values here, we get this series, pi over 2 is equal to 4 over pi times these terms, and then we can rearrange it to get pi squared over 8 is equal to this series, and this series was first computed by Euler in 1748. And so the second thing that we did was we took the derivative of both sides of the equation. And now, since taking the derivative of a function is just finding, I guess, what the slope of the function is at a certain point, if we take the derivative and set x equal to pi, we know that pi lies on the region between pi over 2 and 3 pi over 2, and the slope along that region is always -1. So take the derivative, set x equal to pi, and the left side of this equation turns to -1. And now, for the right side of the equation, we can actually take the derivative of each individual sine term here to get these cosine terms. And then, likewise, with the sine, we actually know what cosine of 3 pi is, cosine of 5 pi, so on, based on how the cosine is defined. And we know this without actually needing to know the value of pi itself. So again, we plug in the values and we get this series here. We rearrange the terms, and we get pi is equal to 4 times this series. And this is called the Gregory-Leibniz series because it is thought to be computed by both Gregory and Leibniz at the same time, independently. And so the last thing that we're going to do for this presentation is, instead of taking the derivative, we're going to integrate both sides from 0 to pi over 2. And again, from 0 to pi over 2, the slope is always 1. So that's the same as integrating from 0 to pi over 2 of x dx, which is right here. And then this can just be computed to be pi squared over 8. Alternatively, if you look at the graph, you can use the equation of a triangle with base pi over 2 and height pi over 2 to get pi squared over 8, since integrating the function is just finding the area under the curve. And so, for the right side of the equation, again, like with taking the derivative, we can integrate each individual sine term from 0 to pi over 2, because again, we know what sine of pi over 2 is and sine of 0 without needing to know what pi is itself. So again, we go through this and then we plug in all of the terms, and we get this series here, pi cubed over 32 is equal to this. And then this was also computed by Euler, but the thing is, these series have been computed before, but how we actually got to these series is different from how they were originally computed. And that is the end of my presentation.
Thanks. Questions for our speaker? One of the things that I do as a physics teacher is introduce students to graphing by having them graph circumference versus radius, for example. Very low level, but it's an introduction to graphing. And one of the things I like to have them do is graph circumference in millimeters and diameter in centimeters. And that changes the value of pi, but it also puts units on it as well, which is kind of an interesting thing to do. I also have done inches versus feet, just to include units on pi rather than have it just be a number. And you're sophisticated what you're doing, but I appreciate what you're doing.
Yeah, when I was going through and creating the graphics for this, I used GeoGebra, and it actually helped me learn as I went and did all the graphics, because I would have to graph everything out, and that helped me learn the material more because it's more visual.
Yes, absolutely, very good. Any other question there?
So, I mean, these frequency generators that you get from Pascal or whatever in the physics lab, they have the different functions now, you know, the sawtooth and the square root. I mean, I think it's fascinating